Hi! During the past few weeks, I have been exploring and learning the Godot game engine. In order to better understand how to use Godot, it made sense to me to attempt to port an already existing project from Unity, since I have some experience with Unity already. I chose Sebastian Lague's Procedural Planet project, since it contains some interesting features like multi-pass post-processing effects and compute shaders. Also, it was relevant for a game idea I'm working on. I started with Godot version 3, which is currently the latest stable version of the engine. However, I quickly realized that it lacked some essential features, so I looked at what is the bleeding edge of the engine and downloaded Godot version 4, which is currently in the beta stage. It offers some new features to the table, like the Vulkan renderer, improved global illumination, high fidelity features like volumetric fog, among others. It also supported compute shaders, which was just what I needed for this project. I started with implementing the terrain. I won't go through the details of how the mesh is created, since Sebastian Lague perfectly describes that himself in his videos. I have mostly just translated the C# code into GT script, with some adjustments here and there to make it fit into the Godot engine. The main difference comes with how the height and shading data is calculated for the terrain, which is based on compute shaders. In Unity, compute shaders are written in HLSL, whereas in Godot they are written in GLSL. Understanding and porting the compute shader code was the biggest challenge for me, since I had not written any compute shaders before. The latest Godot docs has a nice explanation how compute shaders work and how to use them in the engine. Compute shaders run on the GPU split into so-called workgroups. These workgroups reside in the GPU's global memory, either in 1, 2 or 3 dimensions. They have their own local memory, which is a lot faster than the global memory in the GPU, and it is only shared between threads running within that specific workgroup. In other words, workgroups are like independent computers performing calculations without the knowledge of or communication with other workgroups. The threads inside of a workgroup can be referred to as invocations or work items. They can also utilize 1, 2 or 3 dimensions of memory. This means if you want to run 512 threads over a 3-dimensional space, you will have to define the workgroup size as an 8x8x8 cube. Based on various resources online, one of them being Nathan Reed's response in the following Stack Exchange topic, the number of threads should be a multiple of 64 to fully utilize the GPU performance for parallel calculations. In the general case. This is because workgroups have a minimum physical size, which varies depending on which GPU you have. AMD GPUs perform 64 threads wide operations at a time, whereas NVIDIA GPUs performs 32, no more, no less. Regardless, there are a lot more factors in play when it comes to optimizing performance in compute shaders. What I went through is just the tip of the iceberg. The best approach is always to try out some different combinations of workgroup sizes to see which one gives the best performance for your application. Now that we have this information, let's have a look at our compute shader code. In order to send information back and forth between compute shaders and our main program, we define layouts. The first layout we define is the workgroup size layout. Here we define the number of threads in up to 3 dimensions of the workgroup local memory. The dimensionality of the workgroup size should be the same as the data you are trying to manipulate. For example, if you are going to work with 2D textures, you should create a 2-dimensional workgroup size. In other words, set both the X and Y values of the workgroup size layout. Next, we have the vertices and heights layouts. The vertices layout is read-only, whereas the heights layout is write-only. This is because the vertices buffer is our input and the heights buffer is our output. The data is stored as a float array for both the vertices and the heights. Every 3 values of the vertices data corresponds to 1 vertex's x, y and z coordinates. The bindings should be unique for each layout. This tells them apart from each other and enables us to map the data from our main program to our shader program correctly. We also define our parameters as buffers to their unique binding. There are probably better ways of doing this, but this is the method that worked as expected between Godot and the shader program. In our main function, our actual processing is done. We can fetch our current global invocation index via GL global invocation ID. We choose the X parameters since we are only dealing with one dimension as our workgroup size. We first make sure that we are not going to overexceed our input data. This check should in general always be done since your input data will most likely not be a multiple of 32 or 64, like what is defined as the workgroup size. Naturally, this means that some threads will not be doing anything useful when there are fewer vertices to process than there are threads running. After that, we assemble our vertex data from our vertices data buffer, using the global invocation index corresponding to the current invocation. The next section is mostly a port from Sebastian Lague's code, except for the last line where we set a height result to the corresponding index in our height buffer, which will be our output. OpenGL's wiki page provides a good explanation of compute shaders, so I recommend to have a read if you want to learn more. Let's have a look how to run this compute shader from Godot. Here is a height module, which handles the height calculations for each vertex of our planet mesh. We have some parameters to play around with, like continent noise, mountain noise, mask noise, and more, to change the appearance of our planet. We start by instantiating a local rendering device in the Godot rendering server. When the run method is called, we load our compute shader code into memory. We then convert our vertices array to a byte array and do the same for the heights array after we have instantiated it. The heights array is at this point empty, and our mission is to fill it. We then prepare our parameters data by putting them into an array before we convert the parameters data to a byte array. Then, we create our vertices storage buffer. The size of the storage buffer is in number of bytes. In this case, we use 32-bit floating point numbers in a 3-dimensional vector to describe one vertex. 32 bits is 4 bytes, so it becomes 4 times 3. Then we multiply that by the total amount of vertices in our mesh. We also create a height storage buffer for the output. Its size is also based on the number of vertices, but since it's one-dimensional, we just multiply the number of vertices by 4, again since we're dealing with 32-bit numbers. Then, we create our parameters storage buffer in a similar fashion. Lastly, we set up our uniform set, which contains all our created storage buffers. Our data is now ready, and we can soon send our shader to the GPU. We create a compute pipeline with our shader as input. Then we bind our uniforms to it, together with a compute list. In the compute list dispatch, we specify how many global workgroups we should have, up to 3 dimensions. The global workgroup count should be the total number of data points to be computed divided by the local workgroup size for each dimension respectively. Then we seal that value to keep the total higher than the data we want to process. Finally, we submit our shader to the GPU and sync with it to be able to fetch the resulting height data when the height calculations are done. I then started to implement the Ocean, which is a post-processing effect utilizing ray sphere casting. In Unity, we can render post-processing effects to something called render textures. Godot, on the other hand, does not have render textures. The documentation for advanced post-processing states that a workaround for this is to create a billboard quad mesh and project it onto the camera clip space. Then we fetch the screen texture, do our post-processing based on that, and then apply the result in the fragment shader of our billboard quad mesh. This requires a separate camera, mesh and viewport for every post-processing effect we want to do, which will heavily affect the performance in the end, but I will come back to that later. For the Ocean effect, I had some issues in the beginning with how the linear depth was calculated between Unity and Godot. Luckily, the Godot community on Reddit could help me figure out what was wrong with my code. I decided to do some additions for the ocean effect, so I added foam based on this guide by Owen Deery. The other addition I added was water refraction. I based it off of this shader code found on GitHub. For the atmosphere, which is also a post-processing effect, the main challenge was to figure out how to generate the optical depth texture using compute shaders in Godot. Since there was no documentation how to do this in Godot docs, I went looking for similar issues that people have had in different forums. It took a while, but I was finally able to put the pieces together. When I thought I had managed to get the atmosphere working, I stumbled upon the first issue. For some reason, there was an annoying sphere in the middle of the planet. After some fault tracing, I found out how to get rid of it by adding a small epsilon value to the UVX coordinate in the optical depth baked function. Now the sphere was gone, but there was also some strange artifacts appearing at the far end of the atmosphere, where there were no light reaching into it. I figured it might be some issue with the scattering points, and confirmed this when changing the number of scattering points of the atmosphere. My solution to this issue was to check if the scattering point direction was pointing toward the sun with a given threshold. If so, I will not add the scattered light at that point. This caused some clipping to occur at the far end of the atmosphere, but I thought at least it looked better than before, so I went with it. Now it was time to add the stars. I decided to make the stars a little bit more interesting by clustering them a bit with simplex noise and adding some color tint to deform the clusters. In order for the stars to be drawn correctly, I had to draw them after the atmosphere post-processing effect was applied. This meant that I had to add a separate viewport and a camera just to draw the stars. This was necessary since I wanted the stars to only show up at night. I ended up with 4 local viewports in the scene, each of them having a separate camera. I put them in canvas layers and ordered them from top to bottom, where the bottommost canvas layer is drawn on top of the previous one. For each viewport, I take its texture and provide it to the next processing step. This makes it possible to add post-processing effects on top of each other. Now the planet was complete, with its terrain, ocean, atmosphere and stars. At this point, I started noticing some critical flaws in the Godot engine for this project. The FPS performance was really bad thanks to all the viewports and cameras I had to use. Just adding the ocean post-processing effect halves the FPS in-game. When adding all the effects up, Godot runs at a disappointing 90 FPS. For reference, Sebastian Lague's project in Unity runs at around 600 FPS. I realized that using viewports in this way is not preferable, and there has to be a better solution. I found that people had since before asked for multi-pass post-processing capabilities in the engine, but there was not much progress in the discussions. This issue, for example, is from 2 years back. When reading up a bit more on compute shaders, I thought that it might be possible to implement the post-processing effects in compute shaders instead, and apply them to a texture that is propagated between the different passes. This would then be a bit more similar to how it's done in Unity. However, I realized that for this to work, I would have to be able to write to the viewport texture, and I would have to be able to fetch the screen texture, depth texture, and all of the required transfer matrices to do the calculations for these post-processing effects. If you have some ideas of how to approach multi-pass post-processing in Godot, or if you think there are better ways of doing it with viewports, please leave a comment below. I am very interested in hearing about other solutions to this problem. If you want to try out the project for yourself, I put a link to the GitHub repo in the video description. To sum it up, I learned a lot during this project, and I also found some flaws in the Godot engine when it comes to post-processing effects in 3D. Has this made me want to go back to Unity? Well, maybe. It depends on the needs I have for future projects. If I do need custom post-processing effects for any of my future projects, unless we get good support in the Godot engine, I will probably go ahead with Unity. Other than that, I think Godot is a great engine, and I had a blast learning how to use it. Godot has some nice advantages over other engines that makes it an attractive alternative for me. Anyways, that is the end of this video. Thanks for watching.